Take a look at this handwritten digit. It's clearly a 3, right? Your brain instantly recognizes it, even with its unique quirks. But what does it mean for a computer to recognize this 3? How does it go from a jumble of pixels to confidently saying, yes, that's a 3, not an 8 or a 2? This question is at the heart of many powerful AI tools we use today, from smart study apps that grade your homework to advanced image recognition systems. Understanding how a computer sees is the first step to truly understanding how these tools work. Welcome to our series on the foundational concepts of AI and machine learning. In this first lesson, we're going to peel back the layers and build, piece by piece, the very simplest mechanism a computer uses to make sense of something like our handwritten 3. So, how does a computer even begin to see our 3? Well, it doesn't see it like you or I do. A computer understands numbers. So, the very first step is to turn our image into a language the computer speaks, numbers. Imagine our 3 isn't a continuous line, but rather a grid of tiny squares, or pixels. Each pixel can be assigned a number representing its brightness. For simplicity, let's say 0 for completely black, and 1 for completely white. So, our handwritten 3 becomes a large grid of numbers. A 28 by 28 pixel image, like many used in digit recognition, becomes 784 individual numbers. This grid of numbers is what we call our NLT, yellow and GT, input and LT/yellow and GT. Now we have our 3 represented as a list of numbers. But how do we go from this list to a decision? How do we tell if this specific arrangement of numbers looks more like a 3 than, say, a 7? We need a way to emphasize the parts of the image that are most characteristic of a 3. Think about what makes a 3 unique, those 2 distinct curves, one on top, one on the bottom. To do this, we introduce the concept of NLT, yellow and GT, weights and LT/yellow and GT. Imagine another grid, the same size as our input grid. Each square in this new grid holds a number, a weight, that tells us how important that corresponding pixel is for identifying a 3. Pixels that are typically dark for a 3 might have a high positive weight. Pixels that are typically white for a 3 might have a high negative weight. And pixels that don't really matter, like those in the corners, might have weights close to 0. Now, for each pixel in our input image, we multiply its brightness value by its corresponding weight. This is like saying, how much does this pixel, with its specific brightness, contribute to our 3 score, given its importance? After multiplying every pixel value by its weight, we're left with a new grid of numbers. Each number now represents the weighted contribution of that specific pixel. But we need a single score, a single number that tells us, how much like a 3 is this image overall? So, we simply add up all the numbers in this new grid. This single number is our initial score for how much the input image resembles a 3. But sometimes, we need to adjust this score slightly. Maybe we want to make it easier or harder to classify something as a 3, regardless of the input. This is where the NLT, yellow and GT, bias and LT/yellow and GT, term comes in. It's just a single number that we add to our total sum. It acts like an adjustable baseline, shifting our final score up or down. So, our process so far is, take the input pixels, multiply them by their respective weights, sum all those products, and then add a bias. This gives us our final raw score. Now, let's put this into a more formal, but still intuitive, mathematical language. Our input pixels, represented as a vector and LT, blue and GT, X and LT/blue and GT, are multiplied by our weights, represented as a matrix and LT, green and GT, W and LT/green and GT. This multiplication and summation is often called A and LT, yellow and GT, dot product NLT slash yellow NGT, or NLT, yellow NGT, matrix multiplication NLT slash yellow NGT. We then add our NLT, yellow NGT, bias NLT slash yellow NGT, term, NLT, yellow NGT, B NLT slash yellow NGT. Finally, we need to turn this raw score, which could be any number, into a clear decision. Is it a 3 or not? For this, we use an NLT, yellow NGT, activation function NLT slash yellow NGT. For simplicity, let's imagine a very basic activation function. If our score Z is above a certain threshold, say 0.5, then we classify it as a 3. Otherwise, it's not a 3. So, our complete, simplified model for detecting a 3 looks like this. NLT, red NGT, Y NLT slash red NGT, equals the NLT, purple NGT, activation function NLT slash purple NGT, applied to the result of our NLT, green NGT, weights NLT slash green NGT, multiplied by our NLT, blue NGT, input pixels NLT slash blue NGT, plus our NLT, yellow NGT, bias NLT slash yellow NGT. Now, let's bring it all together with our handwritten tree. The image is converted into a grid of numbers, our NLT, blue NGT, input X NLT slash blue NGT. This NLT, blue NGT, input NLT slash blue NGT, then interacts with our predefined NLT, green NGT, weights W NLT slash green NGT, which are designed to highlight the features of a 3. All these weighted contributions are summed up, and our NLT, yellow NGT, bias B NLT slash yellow NGT, is added, giving us a raw score NLT, red NGT, Z NLT slash red NGT. Finally, this score NLT, red NGT, Z NLT slash red NGT, passes through our NLT, purple NGT, activation function F NLT slash purple NGT, which makes the final decision, is it a 3 or not? Imagine doing this by hand for every single pixel, for every possible digit, for every possible variation of a handwritten digit. It would be an impossible task for a human.